Again, welcome to this introductory episode where we'll be covering sections 1.1, the nature of physics, and sections 1.2, solving physics problems themselves, following along the university physics textbook by Friedman and Young, the 15th edition specifically. So let's get started. Section 1.1, the nature of physics. Now, let's start off with the opening sentence. Physics is an experimental science. Now, our goal in this journey is to take you from not having ever taken a physics course before to covering modern physics like quantum mechanics near the very end of this course. And of course, we're going to be learning a lot of things along the way. We'll be using algebra, calculus, multiple integrals. It's going to be a lot of fun, I promise you. But we have to start off at the basics, and that's what this video is all about. So let's just cover an experimental science. What does that mean? Well, what that means is that physicists, they observe and then they try to explain. Now, some examples of this might be the center of the so-called universe, as the ancients knew it back then. You might have heard this, but it was a question of whether or not the Earth revolved around the sun, or did the sun revolve around the Earth? Another way to phrase this is, was the Earth in the center of the quote-unquote universe, or was it the sun? And in order to settle this quarrel, physicists had to make observations about the sky, they took measurements, and they used mathematics to sort out the patterns that they saw in the measurements, and eventually they came out with the answer that the Earth revolved around the sun. And these attempts at an explanation are what we like to call theories. Now, there are two important parts of a theory that I'd like to share with you. Number one, they can be disproven, which is, I hope doesn't come as a surprise to you. You make a guess about something and you're either right or wrong. But number two is the really interesting one, and the one that I hope bothers you a little bit, and that is that they can never be proven to be correct. Now, I hope you find that interesting, because I love that. I love that. And I don't know why, but I just do. Let's take an example. All right. I sort of want to help get this into your brain. So imagine that this oval I'm drawing is a pond. And let's say you come up with a theory that explains the behavior of this pond. Okay? That makes sense. Simple enough to understand. Now, let's say that scientists, 60 years down the line, study an ocean and they come out with a bigger theory that can tell the behavior of the ocean. And to their surprise, when they sort of apply their theory to your pond and they put the boundary conditions of your pond into their theory, it works. Now, what we can take away from this is that sometimes our smaller theories are really part of a bigger theory that we won't know until further down the line. And so the point in this is that a theory can always be revised and expanded upon, or it can be disproven. And that's a very, I find that just absolutely lovely, interesting. I don't know why. But that's pretty much going to be it for section 1 of the nature of physics. And now let's move on to section 2, solving physics problems themselves. Now, this section is one that I really like. First, we're going to sort of go along with the textbook, what it says, and then I'm sort of going to give my own interpretation and my own advice. So, what you come to see and experience, and maybe you already have, is that physics is daunting. Now, you're going to experience that a lot of times you'll come at a lecture and you'll think to yourself like, wow, I really understood that concept, that seems simple, that was easy to understand. And then you go home and you come and you find out after looking at the homework, you're like, oh, how do I do this? Because surprisingly, what we learned in lecture can turn out to be much more complicated than we thought once we apply it to actual problems. And so the point to take away from this is that learning concepts is the starting point. It's a very important point, but it's the starting point. Now, don't get me wrong. The concepts are going to make up a big part of your knowledge, and they are what is going to help you pass your class, but also understand physics itself, and by understanding physics itself, the world itself. So these concepts are truly important. But taking it to the next level, and applying them, that's where you really reinforce what you've learned. That's where you'll get to see the nuances. You'll get to see that what you once thought was simple, that you actually missed out on the little details, the minute case scenarios. Now, that's what the physics textbook covers. And one more thing it says is that a strategy to help solve a lot of problems in physics, and pretty much what we'll be doing throughout this textbook, is using idealized model, in particular, the point particle model. Now, the point particle model is an attempt to turn a complex problem like analyzing the movement of a baseball and turning it into something simple, like analyzing the movement of just a single dot, a point, a particle, if you will. Now, why do we do this? And first of all, what even is a model? So, a model is a simple representation of a complex system. Or it doesn't even have to be complex, of a physical system. Now you might be asking yourself, well, what's the difference between analyzing the baseball and analyzing just a point? So let's cover that. So when we analyze the movement of a baseball in space, in the air, we have to take into consideration that it's not a perfect sphere. Its weight changes as it goes through the air. The air itself applies air resistance. There's also wind resistance. There is a difference, I know. And the ball is spinning as it moves. So there's rotational motion. Now, if you were to take everything into consideration, it turns out to be a really complex problem. But when we stop and we just treat the ball as a point, we disregard its shape, its weight, and the fact that it's spinning. And in a lot of problems, we also disregard air resistance and wind resistance. And it turns out that we can get a pretty good approximation despite not really analyzing what truly is the real world. We can still get a pretty good approximation. And that's good news. Now, the touch that I would like to add to all this, my own touch, is to enjoy your journey. I imagine that most of you are just starting out in college. These are the years where I would encourage you to see everything with your own eyes and touch everything with your own hands. Now, what I mean by that is to pretty much go out into the world and form your own opinion of things. This is both life and physics advice. Question everything in physics, come out to the problem, to the right answer, your way. Make sure you understand what you're working with. And in life, simply do the same. Question everything, form your own opinions about things. Follow what you believe in. Do what you want to do. Pursue your interests. And with that, I would like to leave you. This has been section 1.1, the nature of physics, and 1.2, solving physics problems. In the next episode, we're going to be talking about units and how we convert between units in sections 1.3 and 1.4. Later.